Okay, so we're just going to review for the second circles test, which covers 5.5 through 5.7 for Geometry 22 and 5.5 through 5.8 for Geometry 21. So 5.5 was called chords and arcs, and there were basically three concepts here. The first concept deals with the length of a chord. If you have two chords that are the same length, so like here and here are the same length, this one and this one are the same length. What these theorems said, and I think there were three theorems, but they all basically dealt with the same thing. What they said was, if the chords are the same length, then the arcs are going to be congruent as well, okay? And the central angles are congruent as well. So in all these cases, angles, chords, and arcs are all matching because they're the same size. All right. Concept 2 also dealt with congruent chords. If you have two chords in one circle that are the same length, then they are the same distance from the center of the circle. Remember, distance to the center, or distance from a point to a line, always is measured along a perpendicular. So if you see a right angle there, that's giving you the distance to the center. The distance to the center is the same if the chord lengths are the same, and vice versa. They might tell you that the distance to the center is the same, and you can conclude that the chord lengths are the same. So that had like a theorem and a converse, but it's all the same concept. Equal chords are the same distance from the center. All right, concept 3 was this idea where if you have a chord that's being intersected by a segment or another chord, there's three things in this concept. There's three things that are happening in this scenario. One is that the segment goes through the center, so it's either a radius or a diameter. The other one is that this chord is cut in half, so it's bisected. And the third thing is that they're intersecting each other at a right angle. And if you remember, these theorems basically said if any two of these are true, then the third one's going to be true too. So sometimes that just helps you mark things in a diagram. In other words, if they give you a segment that goes through the center and you see that the chord is bisected, you can draw in the right angle. Because if two things are true, that last thing has to be true as well. And all the scenarios are true. If you have the chord bisected and it's perpendicular, chord bisected and perpendicular, then you know this has to be going through the center. So even if there was no dot there showing you the center, if those two things are true, bisected and right angle, you can assume that it's a diameter because of these theorems. And then, of course, the last scenario, if this one and this one are true, right? So if it goes through the center and it's a right angle, so all you see is this and this, then you can mark those congruent. Okay? All right. Remember that this is the part where sometimes you have to draw in a radius and use Pythagorean theorem, okay, to find missing parts. All right, 5.6, angles with the vertex on the edge of the circle. So there's two types of angles with the vertex on the edge of the circle. One is called inscribed angles, right? Vertex is on the edge. This is always going to be true. That angle is half the measure of its intercepted arc. There were the three corollaries that went with it. I feel like we've talked about these a lot, but I'll quickly go through them, right? Two angles with the same intercepted arc have to be congruent angles. So the measures of A and B are the same because they have the same intercepted arc. Also, if an angle is half the measure of its intercepted arc, if the inscribed angle has a semicircle as an intercepted arc, then the angle has to be 90 degrees, right angle. Notice that diameter is going to give you that clue there that it's a semicircle. The last corollary says opposite angles are supplementary. So A and C add up to 180, B and D add up to 180, etc. Also in that section, angles with a vertex on the edge of the circle. The other type of angle looks like this. It's formed by a tangent and a secant. Tangent and secant. Not called inscribed angles anymore, but it's the same formula. So anytime you have a vertex on the edge of the circle, that means it's 1/2 of its intercepted arc. These are the ones that I feel are helpful to think of like the alligator. Right? The alligator is chomping on this piece of the circle. The alligator's mouth is open 1/2 the number of degrees as the arc it's swallowing. Okay, equations of a circle in the coordinate plane. Remember to switch the signs when you're writing the center, or if you have the center and you're writing the equation, remember that it's r squared in the equation, so if they want radius, you have to take square root. Completing the square, you guys remember how to do that, right, with the blanks. 1/2 of the middle term here, and then square it and put it here, right? 1/2 of this middle term is 3, so you put it in the equation, square it, and you fill in the blank. 1/2 of -4 is -2. You put that in the equation, square it, and you put that in the blank. Remember, whatever you add to the left, you have to add to the right. Okay, and also you have to make sure everything, all the numbers are on one side and the variables are on the other side. So that's it for Geometry 22, but for 21, you guys learned 5/8. And this was angles and segments. So with angles, remember that a central angle has a vertex at the center, and then those arcs is going to be the same measure as the angle. So if this is 60, then this has to be 60 as well, right? Inscribed angles were 1/2. We just talked about that, right? If this is 60, that would be 30. But what if it's just randomly floating around the middle of the circle somewhere, not in the center, but somewhere inside the circle? Then we said the angle measure is equal to 1/2 add the arcs, x plus y. So when the vertex is inside the circle, you're adding the 2 arcs. Then you have scenarios where the vertex can be outside of the circle, like that, or like that, or one of each. In every case, the measure of angle 1 is equal to the difference of the 2 arcs. So when it's inside, it's adding. When the vertex is outside the circle, it's subtraction. Don't forget that when it's 2 tangents like this, if you call this x, this one could be called 360 minus x, because it takes up the whole circle. All right, and then the last thing, segments, you could pretty much have those same diagrams kind of look the same but as the angles, but now we're talking about the lengths of the segments, right? When its vertex is inside here, you've got A times B equals C times D. Then when you have these situations where you have a secant, or a secant and a tangent, let's do it that way. These are the ones where we said think of outside times whole equals outside times whole. So let's write that. Outer times whole equals outer times whole. So if we put things in here like x and y and w and z, right, our equation would say x times x plus y, because that whole thing is x plus y, and this whole thing is w plus z, equals w times w plus z. So the only thing that's different is with a tangent, remember the whole and the outer are the same thing. So if that's y, whole times outer is just y times y again. That's y squared. Let's call this x and w equals x times x plus w.